In this video, we're going to talk about slope fields. A first-order differential equation is a differential equation where only the first derivative appears. So any first-order differential equation can be written in the form dy dx equals f at xy, where x is the independent variable and y is the dependent variable. We can always replace y and x by different letters, but we always have one independent variable and one dependent variable for this kind of problem. So this gives us a first-order differential equation. A function f in this equation, dy dx equals f at xy, is called the rate function because it tells you the slope or the rate of change of the solution y equals y at x at a given point. So we specify the point y comma x, and then if we evaluate f at x comma y, that gives us dy dx. But what is dy dx? That's the slope of the tangent line. So we call it the slope or the rate of change of the solution. So as an example, let's consider this differential equation. Dy dx equals x minus y. This is a first-order differential equation because we have a derivative dy dx. The rate of change, or rather the rate function, is the function f at x comma y is equal to x minus y rather. So x minus y is the thing that's equal to dy dx. So if you solve for dy dx, whatever that's equal to, that's going to be your rate function. So I'm calling that f at x comma y in this example, and f at x comma y is equal to x minus y. Even if we don't know the exact value of y at x, or that is to say, even if we don't know the exact formula that gives you y is presumably a function of x itself, but we might not know that. But even if we don't know that, we can still determine some properties of y from the rate function, because the rate function will tell you the slope of the tangent line at any given point. So in our example above, we can see that dy dx is equal to 0 at any point x comma y where y is equal to x. We just plug in x equals y into this expression and we get a 0. What does it mean for dy dx to be equal to 0? That means the slope of the tangent line is 0 at that point. So at any point where y is equal to x, our function, our curve, y, will have a horizontal tangent line. So even if we don't know much about our function, y equals y at x, even if we don't know much about y, we know that if y is equal to x, then our function will have a horizontal tangent line there. Similarly, if x is less than y, so if x is less than y, what does that tell us about dy dx? If x is smaller than y, then the result will be negative. So dy dx will be negative. And what does that mean? That means that y is decreasing. If the derivative of y with respect to x is negative, then that means your function y is decreasing. Furthermore, if x is greater than y, then x minus y is positive. So if x minus y is positive, that means dy dx is positive. And what does it mean if dy dx is positive? It means that the function is increasing. So we can conclude that y equals y at x is a decreasing function to the left of the line y equals x, but it's increasing to the right of the line y equals x, because to the right of the line, that's where x is greater than y. Okay, so this allows us to draw something called a slope field, also known as a direction field. This is a graph in the xy plane where the slope of a solution at a given point is represented by a small line segment having that slope. So let's sketch the slope field for the example that we're looking at. So that's this example, dy dx equals x minus y. Here we have an xy plane, or at least a portion of it. And we've made it look like a grid so it'll be easier to plot things. So what we can do is we can select a certain point. For example, we can select the point 1, comma 1. So we can select this point. Now at that point, x is equal to 1 and y is equal to 1. So at the point 1 comma 1, well, y is equal to x there, but we can actually just compute it. dy dx is equal to x minus y, so it's 1 minus 1 is 0. So the slope is 0 there. So at that point 1 comma 1, we're going to draw a little horizontal line segment. Now that represents the slope of the tangent line. So if there's a curve passing through this point, that means it's going to have a horizontal tangent line at the point 1, 1. It will also do that at the point 2, comma 2. So at 2, comma 2, we have the same thing. dy dx is equal to 2 minus 2, which is also equal to 0. So that's going to have a small horizontal line segment there. In fact, any of these points where x is equal to y will have that, even at the origin. If we pick a point where x is not equal to y, we might get a different result. So let's, for example, pick the point right here, 2 comma 1. So at the point 2 comma 1, dy dx is again equal to x minus y. So in that case, it's going to be 2 minus 1 equals 1. So that means the slope at this point is 1. So we draw a small line segment with slope 1, like so. Now there are plenty of other places like that. So for example, also at this point 3 comma 2, we'll have the same thing. At 3 comma 2, we have that dy dx is x minus y. 3 minus 2 is equal to 1. So at this point we draw not a horizontal line segment, a small line segment with slope 1. Now what about, let's say, at the point 2 comma 0? What about this point right there? So at 2 comma 0, we're going to have dy dx is equal to 2 minus 0 is 2. So now it's going to have a slope of 2, which is going to be steeper, sort of like that. And at the point 3 comma 1, it'll be slope 2. So, well, that's a little too much. So it'll be something like this. So the idea here is that we can, at each point, draw a small line segment that represents the slope of the tangent line, or at least the tangent line at that specific point. The point of this is that it gives you some idea of what solutions look like. Some idea, if not a complete idea. In this particular example, notice that along line segments, or along lines, you get slopes of equal value. So along the line y equals 0, let's just draw this in, not y equals 0, but along the line y equals x, all of the slopes are the same. Similarly, let's just change the color here. If we look at, say, y equals x minus 1, which is here, all of the slopes along this line are equal to 1. They all look like this. Along the line segment, let's change the color again. So let's go with blue. Along the line not the line segment, but along the line y equals x minus 2, all of the slopes here are 2. So all of these line segments will have slope 2. So let's just write something like this. So all points have slope dy dx equal 0. The points don't have a slope exactly. We're not saying the slope of the point, but we're saying the slope of the curve at that point. So all points along this line have a solution with a slope dy dx equals 0. And this orange one here, so all slopes are dy dx equals 1 here. And then along this line, which is, so this is y equals x minus 2. So all slopes are dy dx equals 2, and so on. So there's a name for these kind of curves like this. Let me just, so this one is y equals x minus 1. The green one that we started with, this is y equals x. So there's a special name for lines like this, or even just curves generally. So let's move on to the next page here. So the line y equals x, that's this green one here. So this line is not a solution to the differential equation, but all of the slopes along that line have the same value, dy dx equals 0. So a line that passes through points having the same slopes in the slope field is called an isocline. And it sometimes helps to identify them when trying to sketch a slope field like by hand, like we're doing here. Now, it's a line in this case, but more generally it's a curve, so maybe I should even say that. So I shouldn't say a line, maybe I should say a line or a curve, or curve. So a line in this case, but more generally a curve that passes through points having the same slopes in the slope field is called an isocline. And like it says here, sometimes helps to identify them when trying to sketch a slope field by hand. Now, usually you aren't going to generate it by hand. Normally, you'll use a computer. So the following, which we're about to see, is a computer-generated slope field for this differential equation, dy dx equals x minus y. So this is a computer-generated slope field. And you can see that along the line y equals x, which is right along here, all of the little lines have slope 0. They're all horizontal. You can sort of get an idea why it's called a direction field or a slope field now, because you can see that if you connect these line segments up, it gives you some idea what a solution looks like. On the next slide, we have a couple of these solutions plotted. So solutions to the differential equation have graphs that follow along the slope lines. If a solution curve passes through a point, the slope line is tangent at that point. So in this slope field, we have three curves that are drawn in, these solid curves. These are solutions to the differential equation. So the curves drawn over the slope field are here. So the middle one is y equals minus 1 plus x. That's this one, or x minus 1 if you prefer. That's this one right here. The top solution is y equals minus 1 plus x plus e to the negative x. That's this one. That's this one. Notice that we haven't drawn in the xy axes. The x-axis is right here, and the y-axis is right here. They're not drawn in by the computer just to make it a little easier to look at the slope field, but you can put them in if you want. So the top one, the one on top, that's this one, y equals minus 1 plus x plus e to the negative x. The bottom one right here, this is y equals minus 1 plus x minus 2 times e to the negative x. That's this one. So these are three solutions to the differential equation, and you can see everywhere that it encounters or passes through or touches one of these small line segments, you can see its tangent. So let's look at this top curve. You see any place where it touches one of these little line segments, it's tangent. The line segment is tangent. So right here, there's a tangent one. That one's kind of tangent. These ones are almost tangent, as you can see. This one, especially the bottom one, you can see that it's quite tangent to these curves here. So these little line segments represent small portions of tangent lines at these specific points. Let's look at another example. So here we're looking at the differential equation dy dx equals x times y. And here's a slope field. Certain things that you might notice: if x or y is equal to 0, then x times y is going to be 0. So along the x-axis and along the y-axis, you can see that the little line segments are horizontal, representing a slope of 0 for the tangent lines there. You can also, well, let's just go to the next slide where we have some solutions drawn in. So here we have some solutions to the differential equation dy dx equals x times y, and they're written in the order from top to bottom that they're drawn in. So the top one is y equals e to the x squared over 2. The over 2 is in the exponent, so it's x squared divided by 2. So e raised to that quantity, x squared divided by 2. That's this curve right here. Again, the x-axis is here and the y-axis is here. It's just not drawn in because it makes it a little bit easier to see the slope field. So the top curve that's drawn in is y equals e raised to the x squared over 2. So that's this one. The next one is y equals 0. That's the x-axis. So that's a solution to this differential equation. Because any time that if you look at the function y equals 0, then x times y is equal to 0, but it's also constant. So dy dx, if y is constantly equal to 0, dy dx is also equal to 0. So y equals 0 is a solution to the differential equation. Moving down a little bit further, we have y equals negative 1 over 10 times e to the x squared over 2, which is this curve right here. And moving down a little bit further, we have y equals negative 2 times e to the x squared over 2. So in fact, all of these solutions to this differential equation have the form some constant times e to the x squared over 2. And these are just a few of them. Y equals 0 is 0 times e to the x squared over 2. So all of the solutions have that form. And you can sort of see what other solutions might look like just by following these slope fields. And again, that's why we think of them as direction fields, because they, or I should say, that's why they're sometimes called direction fields, because they give you an idea of what direction the solutions are going in. And in fact, sometimes people draw little arrows on them to indicate the direction of motion. One thing that's important to understand about slope fields is that a slope field represents, in some sense, all of the solutions. We're not just looking at one solution to the differential equation, we're looking at all of them. So through each point, we'll get a solution. And we can see what the slope of the tangent line to that solution is at that point. But you can see here that there are many solutions represented. We've superimposed 4 solutions here. But there are in fact infinitely many solutions that would appear on this graph, or that could appear if we just drew them in. And you can sort of see where they would be if you just follow along with these little slope lines. So if we were to pick a point, say this point right here, maybe we'll just, this point right here, there is a solution that passes through that point. And we can look at the coordinates of that point and plug them into the differential equation, x times y, and that will give us the slope of the tangent line at that point. But if we choose a different point, we'll find a different slope of a different tangent line, but it might be on a different solution. So if I pick a point down here, if I pick this point, this formula, dy dx, this is a formula for the slope of the tangent line. But notice that this is a tangent line to a curve, which is a solution. So this is a solution to the differential equation. This is another solution to the same differential equation. If you pick a different point, it will give you a slope of a tangent line, but it might be a tangent line to a different solution. This is one solution down here. This is another solution here. We have another solution here. Indeed, there are infinitely many solutions. So each point will give you the slope of a tangent line, but those tangent lines are tangent to curves, and those curves may represent different solutions to the same differential equation. Okay, let's look at another example. Here we have a differential equation dy dx equals y squared minus y minus 6. This is a autonomous differential equation because the independent variable x does not explicitly appear. Of course, y is a function of x, but what that means is that the rate function only depends on y. In this slope field that you see here, the value x does not appear in this formula. So this is our f of x right here. So f of x I shouldn't say f at x comma y is equal to y squared minus y minus 6. So in other words, the value doesn't depend on which x you're at, it just depends on y. So if you pick a certain y value, like y equals 2, you can see that all of the slope lines have the same slope. If you pick a different y value, like y equals 0, you can see all of the slope lines have the same slope. The x doesn't affect the value. That's because this is an autonomous differential equation, and the independent variable x does not appear in the formula for the rate function. Only the dependent variable y does. And that's why it has this very specific form where for each y value, you get one of these isoclines. For every single different y value, if you fix a y value, you get an isocline because all of the slopes are the same. On our next slide, or our next page, we've superimposed some solutions. So here we go. We have several solutions here. Specifically, we want to look at the solutions y equals -2 and y equals 3. So y equals -2 is here, y equals 3 is here. Let's just scroll back up. Those are these lines, y equals -2 and y equals 3. So you can see all of the slopes are horizontal along these lines. All of the slope lines are horizontal. These are constant solutions. We call constant solutions equilibrium solutions because they don't change over time. If we think of x as representing time in some way, so as x goes from left to right, we think of time as passing. And for a constant solution, as time is passing, the y value doesn't change. So it's in equilibrium. So that's why we call them equilibrium solutions. The non-constant solutions have the equilibrium solutions as horizontal asymptotes. So for example, there's one in the middle here, and as you move to the left, it approaches the horizontal line y equals 3, and as you move to the right, it approaches the horizontal line y equals -2. It might look like it overlaps, but it doesn't. It just gets really close. So these are really close to one another, but they don't actually overlap. You can see that we have a solution up on the top, which as x moves to the left, it gets close to the equilibrium solution y equals 3. As you move to the right, it shoots up to infinity very quickly, very rapidly. The solution on the bottom has similar sort of behavior, but with a different equilibrium solution. So this one on the bottom, as you move to the right, it has an asymptote, a horizontal asymptote, y equals -2. So again, it's getting very close. It looks in our picture like they all overlap, but they don't. That's a failure of technology. If you zoomed in far enough, you would see that these don't actually touch. They just get closer and closer and closer. So these non-constant solutions get closer and closer asymptotically to y equals -2. Now, on the other hand, as you move to the left, this curve drops away to negative infinity very rapidly. This sort of behavior that you see represented in the slope field is very typical of these autonomous differential equations, where the rate function does not depend on the independent variable, at least not explicitly. It only depends on y in this case. And this sort of shape where you have constant solutions called equilibrium solutions, and the non-constant solutions approach them asymptotically, this is very typical of these autonomous differential equations.